Hi there. Today we are going to talk about the mole. The mole, you say? The mole, I say. And no, we're not talking about those cute little fuzzy creatures. Are they cute? I don't know. Maybe they're cute. But we are going to talk about something that is used in chemistry all the time to describe the amount of something that we have. So, this is a common unit that we use all the time in chemistry, and you guys are going to enjoy using the mole in your calculations. So, here we go. We are going to define the mole, talk about why it's useful. We're going to carry out a basic molar mass conversion, and we're going to explain how the molar mass of a compound compares to molar masses of the elements from which it's made up. Okay, so we're going deeper into the atom and the structure of the atoms, but we're talking about how to measure atoms because they're so small. All right, so we've learned the structure is super small, so now we have to come up with a way to talk about these super small things, because these super small things are going to have super huge numbers, right? So here's our mole. Why is it necessary to have a mole? I don't exactly remember where they came up with the term mole. Yeah, I forget what it was. I've read that at one point, but I don't remember why they came up with that term mole. But no, we're not talking about one of these guys. We're talking about a unit of measurement that measures amounts of things. So just like a dozen will tell you that there's 12 of something, a mole is going to tell you that there's a certain number of something. So we use this to count very small particles, to count atoms and molecules. So let's look at what a mole is. All right, our base unit to measure the amount of substance. And basically, you have all this little stuff here. It's the same as the number of atoms of carbon-12 and exactly 12 grams of carbon-12. So what that's saying is that, we did come up with a very reasonable way to talk about what a mole is. It was originally developed from Avogadro's number. And Amadeus Avogadro, who you'll see down here on the screen, he actually did some experiments where he showed how much gas could fit inside a space 22.4 liters big. All right, so this little box is 22.4 liters. And Amadeus Avogadro, he basically said, you know what? We can get this many molecules in a space this big. And so this is of any gas. It's kind of cool. Add STP as long as you're at standard temperature and pressure. And so this number is huge, right? So look at this number, 602 sextillion, 213 heptillion, 670 quadrillion particles, right? That's a lot, right? You're looking here, you're at the millions, the billions, the trillions, quadrillions, pentillions. Did I say pentillion before? I don't think so. Sextillion. Okay, so huge number, but let's make it a little easier to say. Instead of that, let's just go 6.022 times 10 to the 23rd. Okay, and you'll see even on that little box, you might have seen it says 6.023. Let's see, I think it's like that. Yeah, this one's 6.023. Now, why that is the case when that's the number, that number might be wrong. I'm pretty sure this number is right. Should be 6.022 times 10 to the 23rd. But anyway, it's called Avogadro's number, and it's a number that describes a ton, huge amounts of something, right? Well, a huge amount of something like that is not that big. If we look at a huge amount of copper, it's that big. That's it. That's a mole of copper. These atoms are really small, really small. Like if I were talking about a mole of sand particles, right? Tiny little sand particles. A mole of sand particles would fill up the city of Denver 5 miles deep. That's as high as those planes go that you see way up in the sky. The entire city of Denver filled up 5 miles deep with sand. Well, that's a mole. And yet we can fit a mole of these atoms, these copper atoms, into the space this big. Atoms are small. It kind of gives you a feeling for how small they are, right? Really small things. All right. So what we do is we say, there is something called molar mass, which describes the mass of a mole of a substance. Okay, so if I have copper, if you look on the periodic table and you look for copper, you're going to find a number underneath the Cu, and it's going to say 63.55 grams. And that's what this weighs. That's the molar mass of copper. That's the mass of 1 mole of copper. Okay, that's what molar mass is. The mass that it would have if you had a mole of those particles. Okay, and so our units are grams per mole, number of grams per mole of that substance. So for instance, if I had carbon-12, a mole of carbon-12 would have a mass of 12 grams, right? So we just say the molar mass of carbon-12 is 12 grams per mole. Now, we can convert between moles and grams, okay? And the way you convert is by using, this is a small portion of the mole road. In chemistry, you're going to learn a much bigger portion. But we just convert between moles and the mass, okay? And so we can say, hey, if I have a certain number of moles, I'm going to use this little conversion factor, and I'm going to multiply by its mass that we find in the periodic table, and I'll tell you how many grams it is. Okay, so if I said, hey, I have 2 moles of copper, then I would put a 2 right here, 2 moles, and I'd multiply by the molar mass. And so 63.55 grams per mole, I get 127 point something grams of copper if I had 2 moles, right? 1 mole is 63.55, so 2 moles would be double that. Okay, so let's see how we would do a conversion like that, all right? Let's just do a real quick conversion and see what that looks like. Determine the mass in grams of 5.50 moles of iron. So we start with what we're given, okay? I always start out with our givens and our unknowns, right? So we know that we've got 5.50 moles of iron, Fe, and we know from the periodic table that iron is 55.84 grams per mole. So, all right, we got that. Now let's go ahead and plug that value in. What we're looking for is the grams of iron. Let's plug it into a little unit conversion factor. It's pretty easy. Let's just make a conversion factor that would have the denominator and numerator showing those 2 components. Okay, so now I've got 55.84 grams of iron in a mole of iron. Just like I'd said with this one, right? Well, we've got some iron over here. Boom, there it is. It's a little lighter than the copper. Here's some iron. So this is a mole of iron. Notice it's similar to the size of a mole of copper, but check it out. Here's aluminum, bigger, and guess what? It's a lot lighter. Kind of cool, right? The aluminum is a lot lighter, even though it's bigger, because the atoms are a lot smaller in terms of its density, but they space out a little bit more. Sorry, smaller in terms of mass, but they space out more. And that does mean for a lower density too. Okay, so multiply the amount of iron by this conversion factor. So we just start, all right, 5.50 moles of iron, and then we use that conversion factor, and it cancels out, right? So we cancel out moles of iron, whatever we do. Okay, when we do that multiplication and division, we can take the stuff that's on top of the fraction and the stuff that's on bottom of the fraction that's the same, and we can cancel them out. So those units cancel out. And now we have grams of iron as the unit that we're looking for here, right? G of Fe, grams of iron. And we have 3 sig figs, and so we want our final answer to be 3 sig figs. Box that answer. We have 307 grams of iron in 5.50 moles of iron. See how that works? Kind of cool, huh? All right, so that's a unit conversion problem, and that's how we do unit conversion. All right. So now I want to talk briefly about molar masses in terms of compounds, not just in atoms. So we learned about atomic mass, and we learned that we could look at the periodic table and look at the number below the element and the element symbol, and we could say, hey, copper is 63.55, right? And we would say that that is AMUs. If we have a mole of copper, we'd say, oh, well, if I have a mole of copper, it's 63.55 grams in a mole. Well, what happens if I have something like a compound instead of an atom? Instead of just copper, what if I have H2O? All right, so that's got 2 H's and an O. And now I just have to add these up. So it's pretty easy. I just add up all of my different components of my compound. I look up on the periodic table and I find out hydrogen is 1.01. I've got 2 of those, so I multiply 2 times 1.01 to get my mass of hydrogen. And oxygen, I look on the periodic table and it's 16. And so now I add that to my 2.02 and I get an answer of 18.02 grams per mole. So the molar mass of water is 18.02 grams per mole. And it's more than the molar mass of oxygen, right? Because I've got an oxygen plus 2 hydrogens. So the more atoms you put into a compound, the more the mass is going to be, okay? So compounds are going to have a greater molar mass than the elements from which they're made, you know, if there's more than, than that single element. Okay, so let's just practice this real quick. And so you're going to do the pause it and practice. And you're back. And let's talk about the mass in grams of a mole of sodium. Look at the periodic table. All right, you look up there, sodium's 22.99. All right, so 3 sig figs, oh, 22.99 is not going to do it, is it? So we should say 23.0, all right, 22.99. It's going to round that up. Neon, oh my goodness, if I had eyes, I could see that far, all the way on that wall, so far away, right? Neon, 20.18. So we want 3 sig figs, 20.2. Nickel. Nickel is number 28, and it has a mass, molar mass of 58.69. Again, you know, different periodic tables are going to have different numbers sometimes. And so if your number's a little different, you might have looked at a slightly different periodic table than I did. But they're not going to be off by much. They'll be off, you know, maybe by the hundredths, but probably not by the tenths. Which of these samples has more mass? Okay, we had 1 mole of each of those. Which one has more mass? Well, look at this. That's pretty easy. Nickel, right? Nickel has more mass. Which sample has more atoms? Well, now this might have tricked you. This is a question that oftentimes tricks students. They all have the same number of atoms. They have a mole of atoms, right? Avogadro's number, 6.022 times 10 to the 23rd. They all have the same number of atoms because they're all 1 mole. True or false? 1 atom of sodium has a mass of 23 grams. Well, we just did that. Oh, did you see that? Do you see that tricky word right there? An atom of sodium would have a mass of 23 AMU. That's really small, right? An atom is really small. An atom is not anywhere near the size of 23 grams. And so this one's tricky, right? It's not a mole of sodium, it's an atom of sodium. So this one's false. True or false? Carbon dioxide has a molar mass of 32. Well, I've got 2 oxygens. That's 16 plus 16. That's 32. And now I have to add carbon. That's 44. So this should actually be 44 grams and not 32. So that's also false. Cool? Make sense? All right, so let's see if we can now review our objectives, see what we've learned. Can we define a mole? Yeah, it's the SI unit for the amount of something. Why do we need it? Because atoms are really small. And if I want to talk about how many atoms there are in this, it's much easier to say 1 mole than it is to say, right? How many that is. 602 sextillion part of it, blah, 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 right? So it's going to help us to explain amounts of things much, much easier. Carry out a basic molar mass conversion. All right, you can do that now. You just have to use that molar mass, grams to mole, or flip it, moles to grams, either way. And then explain how it compares. Well, the molar mass of a compound is going to be bigger, right, than the molar mass of the element from which it's made. Okay, so now you know a little bit more about the mole. I hope that you had a good time learning about moles. Here are 3 moles right here. They may not be as cute and fuzzy, but mole of aluminum, mole of copper, mole of iron. Oh my, I got another mole. 4th mole, mole of something, zinc maybe. I'm not sure which one that is. Anyway, good stuff. I hope you have a great day. I hope you enjoyed what we learned today. Be kind to one another. God bless you.